So we're going to start with 5.4 and finish these notes. We left off finding the places between which we would find a 0 using a table of values. If you would be so kind as to sketch the following little graph in your notes. Doesn't have to match mine exactly, just a rough sketch. All right, so we have talked before regarding parabolas about a maximum or a minimum, correct? But here, this graph, does it have a maximum? You can talk. No. Why does it not have a maximum? Yeah, it goes up and down forever, right? So there is no one place where we stop and have a minimum value or stop and have a maximum value. However, we do have changes in direction, and so these changes in direction create points that do indeed have names. Here, this red point is called a relative maximum. It's a relative maximum because relative to the points around it, it is a maximum value. Does that make sense? It's not an actual maximum, but it is a maximum in relationship to the points that are in its immediate vicinity. And then, of course, on the other side, down over here, we have a relative minimum. Now, when we talk about graphing and we talk about these points that are relative maximums or relative minimums, they have another name that encompasses both of them. They get called extrema. So extrema in a graph and in a polynomial function are places where something interesting is happening, specifically relative maximums and minimums. Later on, when you get into calculus, this will take on yet another name. They'll be called inflection points, and they'll have, or a point of inflection, and there'll be all kinds of things that will happen at points of inflection, places of interest where things change or interesting things happen according to whatever it is that you happen to be studying. The book describes these points as turning points. We could also refer to these as what? Sometimes we've called these, in a parabola, it would have the name vertex, right? So a place where we change direction, a turning point, right? So that's really kind of all that we need to play with in Chapter 5, Section 4. The big thing here in Chapter 5, Section 4 is realizing that graphing these is going to get complicated, right? We saw in the homework that there's lots of places that we have changes in direction that have nothing to do with your axis of symmetry, or not axis of symmetry, sorry, the solutions, the roots. So this is going to get interesting. And there needs to be ways for us to talk about tables of values and things that we can do to make this life problem just a little bit easier. All right, so that's all I wanted out of 5.4. So now we're going to hop into 5.5, which is where the real fun begins. So 5.5 is all about actually beginning to solve. And so we're going to be using some factoring from the quadratic era, and we have a new factoring thing to bring into the game as well. So here we go. This particular section is 5.5, which is solving polynomial equations. All right, so I'm going to start by introducing two new ways to factor, and the first one is the sum of cubes. So the sum of cubes says that if you have a cubed and it's added to b cubed, it will factor into a plus b times a squared minus ab plus b squared. And likewise, we have the difference of cubes. And the difference of cubes says that if you have a cubed minus b cubed, then that will factor into a minus b times a squared plus ab plus b squared. Note that these two things are almost identical, right? The big thing to note is that when I have the sum of cubes, right, then I'm still going to have a subtraction symbol. It's back here in the trinomial, right? And when I have the difference of cubes, then I still will have a subtraction symbol, but this time it will be in the binomial, and my trinomial will remain all positive. Okay? This, while it is, I guess, sort of considered a shortcut, this is just what you have to learn and memorize and use. Right? There isn't like another way to make this work. And I think I just shoved words on top of each other, didn't I? That's exciting. There we go. That's better. All right. So let's try one, shall we? Let's take 16 x to the fourth plus 54 x y cubed. And let's factor this. Yep.
54 or 5?
4. You didn't see that 4 up there?
No.
Okay. So 16x to the fourth plus 54xy cubed. All right. Now, first and foremost, we should always look for what?
Perfect square.
No. Yeah, Arshdeep? GCF. No matter what, you always want to be looking for a GCF. And so, is there a GCF in this particular problem? What is it?
16x.
No. Yes.
4x.
No. Yes.
2x.
2x. Right? 54 is divisible by 2, but not by 4. And 16 is also divisible by 2. Right? And then there is an x in each term. So I can factor out a 2x. And when I factor out a 2x, what am I left with? 8x cubed, and then plus what? 27y cubed. Now, in the past, at this point, we would have said, yes, start looking for perfect squares, right? And then if we didn't find perfect squares, we'd be done. But now we've introduced the sum and the difference of cubes. So we obviously don't have perfect squares here. But do I have perfect cubes? Is 8
Yes.
a perfect cube? What is the root of?
2.
All right. So this becomes 2x. All right. What about 27? Is that, excuse me, a perfect cube?
Yes.
3, right? And then y cubed, of course. So we have 2x and we have 3y. That is my a and b from my generic form from up above. So from here, we can start to factor. So we still have that 2x that's sitting out front, right? That hasn't changed. But now we can write a binomial that is 2x and then plus 3y. And then I get a trinomial where I take a and I square it, right? So a squared would be 4x squared. And then we're going to subtract, and then we're going to take a times b, and a times b would give me 6xy. And then we're going to add b squared, which would be 9y squared. And this is the sum of cubes factored. Yeah. So I'm looking at 8x cubed and asking myself, is 8 a perfect cube? Is there one number that I can multiply times itself 3 times? And the answer is yes. 2 times 2 times 2 will give me 8. And then same thing for 27. Is there a number that I can multiply times itself 3 times to get 27? And the answer is yes, 3. 3 times 3 times 3 will give me 27. Does that make sense? Yeah. Your calculator will handle cubic roots, so you can plug that into a calculator. And if you need help figuring out which buttons, we'll do that. I can certainly help. But also, hopefully, most of the numbers that we'll be dealing with, it shouldn't take that long to figure out what number that might be. All right? Most of the perfect cubes that we'll play with probably today are numbers that you'll be relatively familiar with. Does that make sense? Good question. All right. So then this is factored. You should always check, right, on that trinomial. But these trinomials are not going to factor any further when we get them out of the difference or sum of perfect cubes. They're not going to go any further than where they're at right now. All right? Should we do another one? I think we should do another one. Let's do another one. Let's try. How about 5y to the 4th? We'll make this example number 2. 5y to the 4th minus 320 y z cubed. I know, right? Okay, so GCF 5y. So I'm going to pull a 5y out, and when I am done, I'm left with y cubed. And then 320 divided by 5 will give me 64. And then we have z cubed. So looking at my binomial, this is a difference. So I should kind of look for perfect squares, but obviously y cubed is not a perfect square. Do I have perfect cubes? Yes. What do I multiply times itself to get y cubed?
1.
Y. What do I multiply times itself to get 64? 4. 4 times itself 3 times will give me 64. And then, of course, my z. All right, so here we go. We've got the GCF. It's still sitting out there. Then we can write my binomial. And this time I have a subtraction in the middle, right? So I'm sitting here with a subtraction symbol. And so that means that according to the difference of cubes, if we go upstairs and look at that, oh, careful, then we have the minus sign in the middle. You can see that one here. When I have a subtraction here, I get a subtraction here. If I have addition here, then my subtraction goes in the trinomial. There's always at least one minus sign in my factor when we do this. All right, so let's finish here. So from here, I've got my binomial y minus 4z, and then my trinomial squares a, which would be y squared. Then I take y times b, which will give me 4yz, and then we square b to get 16z squared. All right, and from here, we're done, and that's factored. Does that make some sense?
Yes.
Feel all right with this? This is straight memorization, right? There's not like a trick to this. There's nothing else that we can do to factor these at this particular point. There are, of course, some ways that we can go further than this, but right now, this is the only way that you know to factor and to get this information out. All right, so let's check factoring by grouping, just to make sure that you guys are okay with that. We've done factoring by grouping in the past, but I do want to make sure that you remember how this works. So this one is factoring by grouping. So factoring by grouping is what we might play with if you have 4 or more terms in your polynomial, right? If we have a binomial or a trinomial, we have things that we can do. As soon as we hit 4 or more, then currently our only method is to try factoring by grouping. So let's play with this one. How about we do 8, that's an 8, 8ax plus 4bx plus 4cx plus 6ay plus 3by plus 3cy. I know, lots of terms. Always look for like terms. Do we have any like terms? No. This is about as simplified as this one gets, right? Okay. So basically I'm looking to group stuff together when it comes to factoring by grouping. So do we see 2 or more terms that might be good for grouping together? Yeah. The first 3. Why would you group the first 3 together?
Because they all have x and they're also all divisible by 4.
Very good. They all have an x. So I'm going to take those first 3 terms, and I'm going to group them together, and as noted, they're all divisible by 4, and they all have an x. Is there anything else that they all have in common, or a GCF? All right, so when I factor that out, what am I left with?
2 plus b plus c.
2...
2a.
2a plus
B plus C.
b plus c, right? Then that leaves me with the last 3 terms, and if I group those together, what can I factor out of that? 3y. So it's a positive 3y, and that leaves me again with 2a plus b plus c. When we factor by grouping, the big thing to remember is that this is only going to be successful if the parentheses are the same, right? So this parentheses here and this parentheses over here, if these match, we're good to go. If they do not match, then we either did something wrong or it doesn't factor, right? In which case we would call it what? Also known as, starts with a P, prime. Also known as prime, right? So, to continue this this would factor into, I always pull out the common parentheses first, but it's not going to matter the order in which you write this. But this will factor into 2a plus b plus c, and then what's left is 4x plus 3y. And so that would be my final answer right there. All right, so that's factoring by grouping. All right, so of course, the next step is to take this information and solve. So, let's see what happens if we put some equal signs in here. I know, it's super exciting. All right, so let's play with 18x to the 4th minus 21x squared plus 3 equal to 0. All right, so this is an interesting method that they're going to use here. I'm going to show this one to you once. We'll probably not spend very much time on these, but this is interesting anyway. So let's play with this. All right, so what they're asking you to do in this particular problem is to rewrite this in what they call a quadratic form, right? So they're asking for a way to take this and turn it into something that can be squared, and so that you wind up replacing things and getting a quadratic problem. And quadratics you know how to solve, right? So the way that they would solve this particular problem is they're going to look for a way that we can write parts of the two terms with the x's as something squared, right? Something squared. And so when you look at 18x to the 4th and 21x squared, do they share any common factors? What? 3x squared, right? And so what I'm going to do is take this first term, 18x to the 4th, and we're going to rewrite, right? If I rewrite this as 3x squared, and then we square that, what do I get? If I square 3x squared, we get 9x to the 4th. And if I multiply that by 2, what do I get? I get 18x to the 4th. Okay? So I took the GCF between my two terms with x's, and in the first place I squared it. And then in the second place we simply write it down, 3x squared. And then if I multiply that by 7, I get my 21x squared. Does that make a modest amount of sense? We'll do this at least a couple times. And then this is minus. And then, of course, we have plus 3 and then equal to 0. Now, this is the method that they're about to show you is called a substitution method. We're basically going to replace the parentheses with another variable so that we can solve this problem. All right? So I am going to let u, and u is what we almost always use when we do substitution. This is pretty popular in calculus, by the way, u substitution. So let u equal 3x squared. If I do that, I now have the following problem. 2u squared minus 7u plus 3. Which, of course, is equal to 0. Now that should look solvable. Does this factor? Two numbers that multiply together to give me 6, and then add together to give me -7. -6 and -1, right? And so if we use our t-chart or magic beans or whatever we're calling it, right? Multiplied together to give me +6, adds together to give me -7, that's -1 and -6. So we would come in here and however it is that you wind up doing this problem, whether it's guess and check or whether you remember that we would write 2u squared minus u minus 6u and then plus 3, right? And then we would come in here and group, put my plus sign back in the middle, factor out a u, leaving me with 2u minus 1, factor out a -3, leaving me with 2u minus 1, always remembering to set it equal to 0, and then we have 2u minus 1 times u minus 3 equal to 0. And of course, to solve this, now that we have it factored, we have 2u minus 1 equal to 0. We have u minus 3 equal to 0. And when I solve, u is equal to a +1/2, and u is equal to 3. Yes?
Where did you get the 6 from for the chart?
Whenever we do t-chart factoring, it's always A times C, and then B goes here. All right, it's always A times C. Glad you asked. All right. Now that we're here, and I have what u is equal to, now we have to go back and substitute back in the value of u. So now I have 3x squared is equal to 1/2, and 3x squared is equal to 3. And so from here, we simply solve for x, right? So I'm going to divide by 3, right? Which means I'm multiplying by 1/3. So I have x squared equals 1/6. Take the square root of both sides. And now we have x is equal to plus and minus the square root of 1/6, which we're not allowed to have. So we need to go in here and rationalize, right? So this turns into plus and minus the square root of 1 over the square root of 6. Square root of 1, of course, is 1. Square root of 6 doesn't go anywhere. We do, however, have to rationalize. We have to get rid of that radical in the denominator. We're not allowed to have that. To do that, we multiply top and bottom by the square root of 6, which is going to give me plus and minus the square root of 6 all over. What is the square root of 6 times the square root of 6? Say again? Which is 6. That is the whole point, by the way, so that the square root drops out and you're left with whatever's on the inside. Okay, so we just found 2 answers, right? How many possible answers could I have, by the way? 4 possible answers. We have 2 of them. Let's go back and catch the rest of them. So here on the other side we have the 3x squared equals 3. Solving for x means dividing by 3. giving me x squared equal to 1. Square rooting both sides gives me x equals plus and minus 1. It wasn't too bad, was it? It's a little weird, right? It's a little weird. But the big things to keep in mind are, this is called substitution. This is putting it in a quadratic form, right? We find the GCF. That's the biggie. Find the GCF in the two terms that have the x, right? So the GCF between 18x to the fourth and 21x squared was my 3x squared. In the first term, what we're going to do is take that GCF and square it, and then multiply it times whatever's left in order to get to my original. In the second term, we simply write that down and then multiply it by whatever's left in order to get the middle term. Then we do our substitution, which should allow me to begin to factor. We'll have one or two problems like this in today's homework, but this is not a major focus for me, right? Because we are going to be doing other things that will allow us to solve this, I think, in a much cleaner fashion. However, this idea of U substitution, this is good that you're getting this now, because this is a pretty useful tool when we get into calculus. Pre-calculus, calculus uses substitution to make life easier, and then you go back and substitute back in to solve things and to do work. So this is a tool that is good to have in your tool belt. All right, so the rest of today is work time, and so I have a couple of problems that I would like for you guys to work on. Starting on page 346. Let's take a look at numbers. How about 1 through 8? Numbers 1 through 8. There are some primes in there, by the way. So 1 through 8 is factoring. So make sure that you figure out what you need to do there. And then let's do number 11 and number 14. And I think that should be good for now. Okay.